In our universe, all things are driven by energy. Energy powers our sun, our environment, our society, even our bodies. Energy is life. New and profound advances in science and engineering are allowing us to harness this energy abundance in marvelous new ways. To create clean, affordable, and reliable energy for all Californians. The SoCalGas Research Development and Demonstration Program has enlisted an incredible team of experts in science, engineering, industrial technology, and environmental policy to identify, build, and implement these transformational technologies throughout society. Collaborating with the world's top institutions, we have deployed over $73 million on hundreds of groundbreaking projects over the past 5 years. Hyatt Hydrogen, which could enable transporting hydrogen through existing infrastructure to power fuel cell vehicles and facilities. Doosan Mobility Innovation's hydrogen drones that have 4 times the flight capacity of lithium-ion powered alternatives. And hydrogen-powered yard trucks that can move massive shipping loads for 20 hours per day with 0 emissions. These revolutionary projects are saving energy, reducing emissions, and improving air quality, as well as increasing energy safety, reliability, and affordability for all. At SoCalGas RD&D, we believe in clean energy abundance, so we are sharing this pivotal research in order to deploy these innovative technologies across the world. Because energy is life. And we believe a clean energy future will bring a better future to everyone. SoCalGas, Research, Development, and Demonstration. Learn more at www.socalgas.com/RDD.
Hi, everyone. Good morning. Welcome to our SoCalGas RD&D research webinar. I'm your host. My name is Alan Loam, and I'm the Customer End Use Applications Program Lead on the SoCalGas Research Development Demonstration, or RD&D team. For today's webinar, we will be welcoming the Darcy Partners team to learn about the exciting work they did to support our SoCalGas's RD&D industrial decarbonization research strategy. Darcy Partners is a technology scouting and innovation advisory firm that provides their members' companies data analytics, due diligence, and other services related to technology scouting. This early work with Darcy helped prepare us for some of the near-term opportunities related to the Infrastructure Investment and Jobs Act, while strengthening our program alignment with the state's decarbonization goals. And so I'm pretty excited for this opportunity to finally share the great work they did with the public and our RD&D stakeholders. Just as an FYI, today's webinar will be recorded. You can access today's recording as well as our past webinar series on our SoCalGas Research and Development webpage. Before we begin, I'd like to walk everyone through the GoToWebinar toolbar that should be visible to all attendees. Please enter any questions in the questions box. We'll review them during the Q&A session after the presentation. During the Q&A session, we'll also open the discussion for verbal questions. Click the raise hand icon to be called on during the Q&A session. When you are called on to ask a question, we'll first grant you access to unmute. Then you must manually unmute yourself. Please go back on mute after asking your question. Please note that you may have to change or update your computer settings in order to enable your microphone. Please take a moment now to check those settings if you'd like. And finally, you will find a few valuable documents in the handouts box. And so first, I would like to share our commitment to the community. At SoCalGas, our commitment to provide customers with safe, affordable, and reliable service goes beyond natural gas. We are also dedicated to improving the quality of life in the diverse communities we serve. To support this commitment, RD&D staff conducts activities to engage with the community-based organizations or CBOs in our service territory and throughout California, notify researchers, entrepreneurs, and businesses from ESJ communities about their research funding opportunities, whether from SoCalGas RD&D or any of our research partners, share the results from our RD&D projects to inform and educate the general public, and lastly, track and report progress of our equity engagement efforts in our annual report. The SoCalGas RD&D program is divided into 5 research areas that span the entire energy supply chain. From low carbon resources, where they look at renewable gas production, to gas operations focused on the technology development of the operation side of the gas supply chain, to ultimately where we interface with the gaseous fuels from clean transportation, clean generation, and customer end-use applications. In 2022, the SoCalGas RD&D team managed 339 research projects. On average, our RD&D projects generated a 7.2 funding ratio, meaning for every dollar of RD&D funding provided to a project, the project also received over $7 of external co-funding. For example, in 2022, 8 RD&D supported projects were awarded about $18 million from the California Energy Commission. If you want to learn more about our RD&D program, please check our 2022 annual report, which is included in your handouts today. We also provide a Spanish version of the annual report to better connect with the diverse communities we serve. The Spanish version of our annual report is also included in your handouts. Both copies are also available on our website in case you'd like to check them out in the future. Finally, we want to stay connected with our stakeholders in the research community and the general public. Please visit our webpage, where again you can find our annual report. You can find information about upcoming webinars and news about the RD&D program. And please reach out to the RD&D team via email with questions, comments, or research suggestions. We also maintain an RD&D page on LinkedIn and on the CEC's research networking platform, Empower Innovation. Now, without further ado, I wanted to introduce the Darcy Partners team of subject matter experts. Nolan is a managing consultant, he's on the left side of the presentation, at Darcy Partners, where he leads consultancy engagements for various clients in the energy sector. His primary responsibility is to assist clients with decision-making and program improvements. He holds a master's in public policy from UCSD. He is joined by his fellow colleagues Juan, Mora, and Lindsay, who are staffed on the Darcy research team. Juan is focused on research related to energy storage and renewable energy, while Mora focuses on the field of carbon capture and clean fuels. Last but not least is Lindsay, who focuses on the field of hydrogen and low carbon power generation. And now that I've taken the opportunity to introduce and welcome a panel of speakers, I'd like to pass the microphone over to Nolan to lead and navigate the bulk of the presentation. Again, I'm just so excited to have you all here today to share the results of this great project we have with our audience. We did this roadmap nearly 2 years ago, and since then I felt it aged pretty well. Anyways, I'll go ahead and turn over the controls to you, Nolan, so you can get started.
Sounds good. Thank you, Alan.
You're welcome.
Alrighty. So I'm going to go ahead and get us kicked off here. So first of all, hello everyone. Thanks so much for attending, and I hope you all enjoy today's presentation and talk. Also, thank you so much, Alan, for hosting and moderating this webinar. I know webinars take some doing, so thanks to you and your team for putting it together. So today we're going to discuss some research the team at Darcy Partners did last spring to support SoCalGas's RD&D efforts. As you can see, the topic for this discussion is going to be industrial gas decarbonization. So we'll jump right in. We'll start by reviewing the technology-centric approach that Darcy used to form this analysis, and then we'll move on to discuss the 3 priority technical spaces that we identified. So spoiler alert, we're going to be talking about post-combustion CCUS, distributed hydrogen production, and thermal energy storage today. So first, I want to take a moment to acknowledge some of the policy drivers, particularly in the state of California, that are relevant for this discussion. In particular, we have SB 32 and Executive Order B 5518. Those are the 2 primary ones on the left there. There are some other policies also shown, but I'm not going to go too deep on any of them. The graph here on the right, taken from the EIA, illustrates those same major California policies and the impact on decarb that those policies expect across the California economy. So one thing to note is that this graph shows all of the California economy. So today we're going to be zeroing in on that teal color in the middle there, which is the industrial segment of California emissions. So as you can see, there's a ton of work to be done in this space in terms of reducing emissions, right? The net zero goals are pretty ambitious, and so we're going to be moving in that direction. First thing we want to take a look at here is the prevalence of natural gas in heavy industry. So if you look at a breakout of emissions from the economy in California broadly, and then you look at the impact of natural gas within that breakout, it's pretty large, right? So it's like 55–60% of emissions from industry. However, you can also think about natural gas as a fuel switch, right? So the target of a fuel switch in that, you might switch something that's currently leveraging some petroleum resource to natural gas in order to accomplish some level of decarb. So, if you add in petroleum to that mix and you think about the whole environment that natural gas can function in, it becomes pretty big relative to overall industrial consumption. Yeah, so just wanted to take a moment to call out, quite a large number, like 80% of industrial emissions. So at Darcy, one of our favorite ways to tackle a problem is to start by understanding the full scope of the issue, and from there drilling deeper on a particular topic. So we created this framework here that you're seeing on the slide, covering the scope of emissions reduction possibilities in a utility industry context. So as you can see, there are some opportunities on the utility side in the spaces of clean generation. So think like RNG, hydrogen generation, blending, that kind of thing, as well as fugitive emissions, right? So leaks, issues around compressors, stuff like that. On the customer end of the spectrum, you see a whole different scope of solutions, right, and drivers for decarbonization. So I'm not going to run through every single one of these possibilities for decarbonization, but I do want to highlight a couple in particular. So in particular, I'm going to talk a little bit about combustion modification. So we have combustion processes that can be modified to make processes more efficient, right? So essentially, using less gas to accomplish the same task. You also have industrial process modification, right? So you change an industrial process to not utilize gas or utilize less gas per unit of output. So you can identify those industrial process modifications across a wide spectrum of industries. We'll talk a little bit about arc furnaces in a coming slide. Jumping in to take a look at that framework. So this is a graph showing from the Energy Futures Initiative, showing basically the various drivers that we identified in our framework and showing their potential for decarb across the California industrial space, so across the California economy. So the idea here is to look at these individual categories. So you can see CCUS there is the first bar with the largest potential for decarb. And then you can see from there that waterfall chart showing where the other opportunities lie. So you can see the target here is fairly ambitious for 2030, right? So I think it's like a 30% reduction in greenhouse gas emissions. So from there we dive in and start looking at technologies. So we took a technology-centric approach to this problem of identifying priority technical spaces for investigation for SoCalGas's RD&D team. So to do this, we leveraged a really handy database from the IEA. So it's called the Clean Energy Technology Guide. It's basically a list of technologies with classification by industry NAICS, fuel source, relevance for decarbonization, the function of the technology, right? So where it fits in industry. It's a pretty thorough data set. Highly recommend checking it out if anyone is interested in sort of technology level analysis. We started with a pretty large number of technologies, so 400 odd technologies, and then we down selected to those that are related to sort of the gas industry, right? As I mentioned earlier, gas industry can encompass gas, but also various petroleum products that are switching over to gas. Then we broke those technologies down into our quad diagram that you can see on the right. So the idea with this quad diagram is basically to compare the TRL, so the technology readiness level, against the potential impact on decarb. So the EIA identifies the potential impact for decarb of all these technologies. And so we leverage their metric there to identify those with sort of the highest potential for decarb. And then we also wanted to exclude, certain technologies that were too mature for a real hard look by an RD&D team like SoCalGas is. So we identified 34 priority technologies, which you can see in the green box in the upper right-hand corner. From there, we took those 34 technologies, and there were some that kind of were duplicates to a certain extent, right? Very similar technologies within a very similar industry space and function. So we bundled those down, and we got to about 19 technologies that we wanted to take a deep dive on. So in the next slide, we'll take a look at that. So here, we're looking at basically SoCalGas's customer base broken out by industry segment, or you can also think of it as a NAICS code breakout. The idea here is to take each of the technologies that we identified, which you're seeing in these bubbles, and then to match those technologies to the various industries in SoCalGas's customer base where they could be applied, right? So for example, in the bottom right, you'll see that high temp heat electric arc plasma arc furnaces. So that is a very specific industrial technology that's mainly applicable in the metals space, right? And the metals space in Southern California is not huge. So accordingly, they have a pretty low impact on SoCalGas's total customer base, right? Other technologies toward the top of the graph, you can see those are the ones we ended up taking a look at and doing a deep dive on that we'll discuss more. One thing to note is there's a bit of a caveat to this slide, which is that we don't have a perfect understanding of the proportion of total energy use by sector that each technology occupies. So to say that a different way, within the metals industry, we don't necessarily have a great understanding of the percentage of total gas consumption that is occupied by arc furnaces or that function within their value chain. So, to a certain extent, this is an approximation of which technologies are most cross-cutting, which technologies have the broadest impact on SoCalGas's customer base. So you'll note the prominent position at the top of the chart of CCUS technologies, thermal energy storage or TES technologies, and hydrogen production technologies. These are super broadly applicable technologies for a couple of reasons, right? So if you think about it, fuel switching to hydrogen, possible in a lot of settings, particularly with equipment that does combustion on site at an industrial plant. CCUS is possible when combustion takes place on site at an industrial plant, which is pretty common, to do your combustion on site, and then the potential for sort of on-site CCUS installations. The last thing is thermal energy storage, right? Process heat, very common need in industry, and so we wanted to also feature that as a space we'd like to investigate. So, again, going back to our original framework, we pull out the individual spaces we want to explore. So energy storage, fuel switching, in this case, primarily looking at hydrogen, although theoretically you could look at other fuel switching opportunities. And then CCUS. So, those are the areas of investigation that we're going to really prioritize. There were a couple other opportunities that were more niche in smaller segments of industry, but we're going to go ahead and deprioritize those for this discussion. So at this point, I'm going to go ahead and hand it over to my colleague Maura to talk about post-combustion CCUS. Maura, I'm going to go ahead and let you give a brief intro. Go for it.
Great. Thank you, Nolan. Thank you to the SoCalGas team for having us here today. As we will see in the next couple of slides, I'm going to be touching base on post-combustion carbon capture and why we think this is a cool technology for industrial decarbonization. So as we see next, CCS is a topic that has been very broadly mentioned and discussed lately. It basically entails all those technologies that would allow you to capture CO2 from flue gas streams. And as you can see in this slide, we have classified the moment in 5 large groups. The first one is industrial separation. It refers to the gas streams that have high methane and carbon dioxide contents, and that needs to be split out so that you can get only the methane. This is very popular for the oil and gas industry or the biogas industry, for instance. The objective is to clean up a gas stream so that you can keep the methane, as I was mentioning, mainly because CO2 and methane together can combine and can produce a combustion, but that will be very low in efficiency because CO2 does not combust. So basically, you want to have a more efficient gas for that section. We can see that this type of technologies has been implemented in the industry for many years, several times. The oil and gas industry is pretty much an expert in this space, and in the biogas industry, there's also a lot of vendors working here. The second one, whose application is more driven towards ammonia production, boilers, furnaces, and gas turbines, refer to pre-combustion carbon capture. And it's in these type of processes, there is a previous step in which the fuel is turned into a syngas, which is hydrogen rich and carbon monoxide rich. And this allows you to capture CO2 in higher concentrations, which helps economics and lower costs. This is a very good technology, as I mentioned, suited for ammonia production, because in ammonia production, you would need an air separation unit that gets you the nitrogen you need for the ammonia and also helps you get pure oxygen that you would use for the combustion. Similarly to this technology, the third group is oxy-combustion type of processes. And in these cases, you use pure oxygen for the combustion, resulting in a flue gas that has very high CO2 concentrations that are easy to capture. And at the same time, you would also be able to use CO2 as a working fluid, like we would see in many cases. The fourth group, and our topic of conversation for today, is post-combustion carbon capture. This is a technology that consists on basically a plug-in device that you connect to your flue gas towers, and that allows you to capture the CO2 from that flue gas stream. This has several advantages for the industrial decarbonization, and that's why we will focus on this during today's conversation. But before I jump to why we think this is cool, the last group is on direct air capture, and it's a technology that has been mentioned very frequently lately, and it basically entails all those technologies that allow you to capture CO2 from the air so that you can remove it actively. It has gained a lot of interest in the industry lately because the IPCC report lately stated that we need to actively remove CO2 from the atmosphere beyond all the treatment that we might do to our industry. And that's why we speak so highly about DAC, though it also has some disadvantages or challenges, as we will see in the next slide. So basically, DAC is short for direct air capture, and it entails, as I mentioned, removing CO2 from the air. This means that CO2 has very low concentrations in the air, and that's why it's very hard to take it out from. You would need very large facilities, very large in size, high energy consumption, and though there's a rising number of vendors working in a solution for this problem, we still see that as a longer term solution. But when we think about a clean energy transition, there's one key factor to consider, and it's that we have an existing industry with existing infrastructure and processes in place. So we can plan new solutions that are completely brand new. So when you think of a new facility or a new plant, you're taking into account that there's novel technologies that are more efficient, that allows you to produce something that will be more clean with the environment, with less emissions, so less carbon intensive. But there's a ton of technologies that are already out there. You already have your facilities that are in place, and that's why post-combustion CCS makes a lot of sense. As you can see in this slide, post-combustion CCS has a high potential to retrofit in existing facilities, and this allows you to use it in many applications across the industry. Basically, as I mentioned, you need to add a plug-in to your system, and a lot of the vendors that are developing technologies in this space have developed modular solutions that would allow you to capture the CO2 and locate your container-like device in your facility without it using a lot of space, or they're very flexible as to how they can place those that installation so that it fits within the land area that you have available on site. As we move on, I will also be looking into some of the economic incentives that we see in this space, mainly because, as you may know, this is still not the cheapest solution ever. So basically, as moving on, the US government is incentivizing in this type of processes. There are several ways in which we've seen funding in this space, and in particular, the 45 tax Q credit is something that we need to mention and you might be aware of. For the 45 tax Q credit, after the IRA, there were some critical changes to this credit that made it available to the broader audience. The Inflation Reduction Act, as you all know, or may know, has extended the crediting period for 12 years. So you can get tax Q credits that you can see in that table below for about 12 years after the project. It also allowed for transferability of these credits, and you can actually cash them out even if you don't have to pay taxes. So if you're an NGO, if your taxes are lower than what the credit actually allows you, you can get the money from them. Also, the tax-free credit lowered the threshold at which a company can get Q credits. Those would be, you would need to have emissions for 12.5 thousand tons of CO2 per year. That's about 35 tons per day of carbon dioxide. And you can get up to $85 per ton of CO2 captured if you're going to store it, or $60 per ton if you're going to use it. Thereafter, the industry has taken a lot of like a big step in this space, and there's a big momentum all over the world. According to the Global CCS Institute, from 2021 to 2022, there was a 44% project increase. And from 2022 to 2023, there was a 48% increase in projects with 198 new facilities announced. So as you can see, the industry is really picking up in this space. One last thing worth mentioning is that, of course, we still know that there are a lot of challenges in this space regarding technological challenges, economic challenges, safety, political. But luckily, the number of vendors that are working out there are trying to solve all of these problems and kind of alleviate some of them, while having in mind that we want to find a technology that would be economically viable. So moving on, we will jump to our next technology landscape. In this technology landscape, we will focus on the post-combustion carbon capture technologies. And as you can see, there's 5 main groups: solvents, sorbents, membranes, cryogenic, and solid looping. And it should be noted that we did not include the biological type of capture, because as an end product, you get a biomass, so it's more considered a use case than a capture case. Also, it should be mentioned that the last category, solid looping, is a new technology that consists of making CO2 react with different chemicals and materials in a loops process, so that you can get carbonates that are rich in CO2 concentrations. This carbonate can be easily turned back into CO2, or more easily than biomass, and that's why we've included them in here. As you can see, this is a novel technology, and owing to that, we only have a handful of vendors in this space. The rest of the framework illustrates how each of these technologies work and which vendors are developing technologies in each of these spaces, both innovators, so smaller companies that you can see in the first column, or incumbents in this space, which are the second one. Going from left to right, amine solvents are the oldest technologies in this space with existing operations in the industry, and that's why we see so many vendors in here. The positive thing about this technology is that it's well known, it's proven, and we know how the chemistry works. However, amines are very sensitive capture devices, and so we need to be very careful with pretreatment. We need to take off sulfur compounds, and we need to be very careful with temperature of the process. Temperature is also needed to desorb or to release the CO2 from the amine, so that's something else we need to take care of. And that's why we see that there's more innovation in the other sectors, because we want to find other technologies that will help tackle those problems. Secondly, we have adsorbents, which are processes in which CO2 are attracted to the surface of certain materials, either physically or chemically, and the CO2 is liberated in a second compound or in a second process. So that's why we will see the technology working in parallel units. So basically, within this space, we have 3 main groups: chemical, physical, and then others, which are combination of novel technologies like metal organic framework or electrochemical systems. Given the advancement that we see in material development, this technology allows us to have very high CO2 affinity, which helps us lower costs and also lower energy consumption for the system as a whole. The last 2 sectors that should be mentioned are membranes, that are a technology that are picking up in the industry very much based on all the development that we again see in advanced materials. And a lot of the membranes are working with combined systems that basically combine membranes with adsorbents or sorbents in either chemical ways or physical ways that are very interesting. And we've seen a lot of development in this space during this year. And then lastly, cryogenic distillation basically takes into account, it's a physical type of separation that by cooling CO2, it enables it to separate it from other flue gas streams. The good thing to mention about this technology, and should be remembered, is that cryogenic distillation makes sense when you have a lot of CO2 in the flue gas stream. If your CO2 concentration is very low, then it would be too expensive in comparison to other technologies, so you would not really work on that solution. I have a lot more to say, but I know we're tight on time. So after this, I want to give the stage to my colleague Lindsay Motlow, who will be speaking about distributed hydrogen production.
Awesome. Thank you, Maura. So as mentioned by Nolan, one of the areas that we identified as a unique emerging opportunity for research and development is in hydrogen's role in industrial decarbonization. So there's a lot of hype in the hydrogen world right now. I'm sure many of you heard about the recent hydrogen hubs announcement by the DOE and the ample amounts of funding opportunities to propel cleaner hydrogen solutions to commercialization. This slide is relevant beyond distributed production of hydrogen, but I think it's important to give a high-level overview of the bigger picture in the hydrogen space and the role of research and development in making sure that we accomplish this both economically and equitably. So this slide highlights not only the various potential evolving roles of clean hydrogen in the energy transition, some more near-term than others, shown here in the infographic on the right. It's separated by color between electrical and chemical applications. It also shows key action items by players in the space in accelerating market uptake of clean hydrogen in the various use cases on the left. So one hill that I'll die on is eternally emphasizing the fact that hydrogen is not a hydrocarbon. We've been spoiled for decades by an easy to handle energy carrier molecule. So hydrogen will definitely thrive in certain early markets, but with its physical and chemical differences, difficulties in storage and transport, and the nuances of new permitting, enabling infrastructure, it has to be approached strategically and with a broader view of what existing infrastructure exists, what barriers to entry are on the TRL, new infrastructure cost, permitting, and financing side, and what first stage use cases and customers might be the most successful partners for offtake. Investment in development of hydrogen distribution and storage infrastructure is key, as well as possibly more importantly, supply chain and broader infrastructure investments. Additionally, development of regulations and regulation compliance pathways for a fully scaled industry and standardization of processes and systems are hugely important to prevent some serious mistakes that could lead to project delays and issues with public opinion of the technologies. And finally, acceleration of technical innovation through R&D, expansion of the hydrogen workforce, early community engagement are really important to consider and prioritize now in early planning stages of those moving forward with hydrogen. And I think that SoCalGas RD&D holds all of these things as high priority in their own move into projects in this area. So if you look one last time to the right, we're discussing hydrogen and its potential role in industrial decarbonization. There are a few different ways that hydrogen specifically can play a role here. Firstly, and probably the most successful near-term application is anywhere in industry where hydrogen can be used as a chemical feedstock for processes or as a reducing agent. These are industries such as steel production, refining, and ammonia production, where due to the challenges and cost of long-distance storage and transport of the molecule, co-location of production facilities to these industrial off-takers is the best approach in the near term during broader infrastructure build-out. So moving on, I want to highlight the broader spectrum of hydrogen production pathways that exist. Many of you have likely heard of the colors of hydrogen. So you've got blue, green, pink, turquoise, etc. The list goes on. I have to say, I absolutely hate this differentiation. We've created the colors to separate different production methods. So now when you think of green hydrogen, you think electrolysis. When you think of any other feedstock-based production method, we typically assume higher CIs or carbon intensity scores alongside of them. This can be a dangerous over-dichotomization. So on the one hand, I understand not wanting to allow a window for increased hydrocarbon production with the goal of producing clean hydrogen, but realistically, there are many places and situations where hydrocarbon assets or waste exists more readily than water or clean electricity. So considering both near-term, mid-term, and long-term end uses and off-takers of clean hydrogen, alongside the difficulties of wider scale storage and transport infrastructure build-out in the near term, I think it's important to consider our existing infrastructure, assets, potential feedstocks for each off-take location when we're looking at distributed hydrogen production, and focus entirely on lowest possible situation-specific cradle-to-grave carbon intensity. So for this exercise with SoCalGas, we zoomed in on hydrocarbon feedstock to focus on industrial customers that have existing natural gas connections with, of course, an eye on implications of emission sources down the entire process, both up and downstream. But first, I'll zoom back out to a feedstock agnostic discussion of the distributed approach with the next slide. So here I'm going to give an overview of the primary thought process behind choosing a distributed model of hydrogen production versus a traditional centralized production model, with an emphasis on different feedstocks and production types. And then I'll show you the broader landscape of vendors targeting this deployment approach and then we'll zoom in on the technology focus that we chose in this project, methane pyrolysis. So I want to start by giving an overview of the different imagined models for hydrogen production, distribution, and ultimately use as we consider what future clean energy systems will look like with hydrogen in the mix as it's projected to be. So on the left here, you can see the two main delivery models that are being considered. First is what we're used to with existing energy carrier molecules in the industry. That's centralized production and distribution. Even our businesses in the space are built to accommodate the system with upstream, midstream, and downstream operators, often split as separate entities, and large-scale production chosen to take advantage of economies of scale. This is, however, and I think we'll see this more with the nature of hydrogen and some of the safety and handling concerns it brings in physical form, limited by hefty requirements and complexities with permitting and developing individual projects. So with hydrogen specifically, we have the issue of mass infrastructure requirements and complexities with both storage and distribution infrastructure, as mentioned above. And where typically the economics of distributed molecule production might not have previously made sense, we have to, especially for near-term deployments, gauge the cost with the cost of infrastructure retrofitting and additions. So on the right, you can see an example of a hydrogen factory of the future. That's a distributed production approach from the minds of researchers at the Fraunhofer Institute. It's just an example of such a distributed model. It's not how every vendor is approaching it, but one important thing that you should note when thinking about distributed production is that you can work from a number of different production types and several different feedstocks. So I think that opens up potential economic advantage and a bit more flexibility based simply on what assets you have on hand. So first, we can always go the renewables route with hydrogen production by electrolysis. This is a highly incentivized method under the new IRA framework with a couple of electrolyzer types dominating the distributed production landscape, including PEM, due to their fast response time, higher power densities, and compact system design, but limited often by their high cost due to expensive catalysts in part and occasionally high operating costs. AEM systems and alkaline to some extent are being developed for distributed use cases and are ideally suited for areas where electrical energy costs are low and transportation costs are high. Natural feedstock-based processes are great if you already have existing natural gas resources, production, transport capabilities, and maybe want to target high-emission customers on-site through gas decarbonization through hydrogen production. DOE, NREL, and Fraunhofer Institute have developed an optimum design scenario for distributed systems with a number of different optimization parameters, such as skid mounting, mass manufacturing techniques, active component sourcing, or modularly expandable subcomponents that make it a bit more economic and ideally follow a learning curve similar to that of solar. So finally, alternative feedstocks such as waste and biogas have become incredibly popular for distributed hydrogen production models, especially where there isn't access to wind or solar or natural gas resources. In the hyperferment projects linked in this final bucket, modularly expandable subcomponents are being designed that are actually production method agnostic to lower the cost impact. So moving on, I want to show a framework here of vendors that we identified for the SoCalGas team, separated by production type or feedstock use, that are targeting distributed production models at about 200 to 1,500 kilograms of hydrogen a day. Blue and turquoise here are the buckets that utilize natural gas or biogas as feedstock. Green companies are developing electrolyzer solutions and can utilize any form of clean energy production, including nuclear or renewables, plus ultra-pure water. Then finally, we have the other category, which contains vendors targeting waste to hydrogen production technologies. So if you look down the framework, you can see I've included a short description as well as a summary of main implications and general TRL for each category, which I discussed generally in the last slide. But taking a quick look, you can see the blue teal bucket contains tech in the traditional reforming space, where many companies are re-engineering systems, optimizing catalysts, and reducing the complexity of emission streams, opting for skid-mounted and standardized systems to accomplish economic distributed production. In the turquoise or methane pyrolysis space, I've separated by pyrolysis type, and I'll discuss that a little bit more in the next slide. The companies in the green space are also separated by tech type, where I gave an overview of the different qualities of each production method and applicability to distributed use cases in the last slide. And finally, the waste to hydrogen bucket, where you can find companies targeting distributed scale waste to hydrogen production, optimizing on circular economy measures by using feedstock that we want to get rid of anyway. So moving on, for this particular research exercise with SoCalGas, based on existing infrastructure and internal knowledge capital and capabilities at SoCalGas, coupled with the fact that their industrial customer base is connected to natural gas feedstocks, we focused on methane pyrolysis technologies. So methane pyrolysis is simply the breakdown of methane through some activation mechanisms such as heat or electricity into hydrogen gas and solid carbon. As you can see descriptions of each of these methods on the left. So typically this falls into one of three general categories: thermal, plasma, and catalytic. The thermal pyrolysis reaction typically occurs either on reactor walls in liquid metal or in carbon granules. Plasma-assisted pyrolysis utilizes a plasma torch and often occurs over a metal catalyst. There are also newer methods in the last bucket that kind of fit within this category, but also kind of not, and that's microwave pyrolysis, which actually utilizes microwaves to create a type of plasma in the feedstock itself. And then finally, catalyst-assisted processes occur over a metal or carbon catalyst. So note these methods by some vendors will in some way be combined, but this is the easiest way to break it down. So if we're comparing this to SMR ATR, no CCS infrastructure is required due to the innate process sequestration of carbon as a solid. And CCS is typically not cost-effective in the status quo at the distributed scale. This method also has a lower energy consumption at about 30 kilojoules per mole of hydrogen than electrolysis, and SMR, which come in at about 300 kilojoules per mole of hydrogen and 64 kilojoules per mole of hydrogen, respectively. Those are general values, so obviously not necessarily, they're technology dependent. But finally, there's potential economic value as well of the carbon product. So an issue is that if methane pyrolysis were the only method of hydrogen production, we'd already saturate the existing carbon black market with production of only about 10% of existing hydrogen demand. But there are a lot of really interesting opportunities to utilize carbon black in different purity levels in future markets. And next, which is a big one with the infrastructure concerns of storage and transport, you can utilize existing natural gas infrastructure. But again, energy supply footprint and leaks in the supply chain are critical to final emissions. And next, and very importantly, the cost of handling the solid carbon has to be considered for these scenarios. And as mentioned with the market saturation of carbon black, methods to optimize carbon products are being developed to expand potential markets of the product. And finally, we're dealing with the Arrhenius equation. So the high temperatures and processes can lead to operational concerns with material stability, catalyst and reactor wall coking and fouling, where the catalyst itself becomes essentially another feedstock of the process. So this is where I think this technology is at a perfect stage for the type of partnership that RD&D can offer, and offers an interesting opportunity for interested industrial partners wanting to decarbonize with hydrogen. So now I'll move on to Juan, who will be talking to us next.
Hi all, it's a great pleasure being part of the SoCalGas RD&D webinar. I'm Juan Corrado and I'm also part of the Darcy research team, and I'll be sharing with you some of the work we've been doing at our market landscape on the topic of thermal energy storage for industrial decarbonization. So with our first slide, we wanted to show the importance of heat decarbonization. We can see on a global scale that the energy consumption by sector here. So from left to right, taking a look at the first two columns of this graph, we can tell that the industrial sector is responsible for 32% of the total worldwide energy consumption. And at the same time, 74% of that energy is used for heating purposes. So in other words, industrial heat accounts for nearly 25% of the total worldwide energy consumption. So 1/4 of all the global energy being consumed is used for industrial heating. And the concerning part is that only 9% of this energy comes from renewable sources, meaning that the remaining 90% is generated from fossil fuels. So in the aid of decarbonization, it is necessary to make an efficient use of this heat. And to do so, it is important to understand what kind of heat we're dealing with to find the proper technologies to decarbonize that heat. So in the fourth column, heat is classified into three main categories, so low, medium, and high temperature heat. And we can see the processes that are responsible for each of these categories. So it is interesting to notice here that 50% of the industrial heat is consumed in the form of low and medium temperature heat. so up to 400 degrees Celsius, from the textile, plastic, paper, food, and tobacco industries, for example, and the other 50% is used from high temperature processes, so above 400 degrees Celsius. So mostly related to material transformation processes. Now moving to the next slide, we'll focus specifically on the US market. So these two graphs here represent the use of low, medium, and high temperature heat again across different industries in the US. And the main conclusion is that similarly to what we have been saying in the previous slide, 40% of the industrial heat demand is under 200 degrees Celsius or 392 Fahrenheit. And to the right, you can take a closer look at the temperature ranges required by some of the main industrial processes. So we can see that the metal and mineral industries, for example, require very high temperatures, same with the chemical industry, but then the vast majority, especially as can be seen in the lower part of the chart, for the food and beverages, pulp and paper, and machinery and vehicle industries, for example, these require temperatures under 200 degrees again, for approximately 80% of their processes. So it is necessary to be aware that these temperature ranges required by these processes that we are looking to decarbonize. On the one hand, we need to be aware of that, to know which technologies we need to provide that heat from a renewable source. And on the other hand, to select the right vendor and technology to store and manage that heat through a thermal energy storage or test system. So through our next slide, I want to explain where heat generation systems and thermal storage systems take an active role and what markets are being targeted by the main vendors in the space. So taking a look at the upper blue buckets, we divided this into those solutions being developed for front of the meter applications and behind the meter applications. In both cases, independently of the heat source, either if it's from concentrated solar power, heat plants, or waste heat recovery, test systems can be used to store heat and manage it accordingly to the end user's needs. So now these test systems may be able to take that heat as an input directly from a heat source or convert power to heat and then store it. And a main consideration for test systems is this energy conversion capability, namely power to heat and or heat to power conversions. So some solutions have these capabilities embedded as part of the test systems, but others don't. So the latter would then require additional equipment, as for example, a Stirling engine for heat to power conversion. When it comes to front-of-the-meter applications, heat can be used for district heating or power generation, converting that heat to electricity and supplying energy to the grid. And for behind-the-meter applications, heat will be used to supply industrial processes and or for heating buildings. Moving then to the lower buckets following the orange coding for heat generation and waste heat recovery, you can see on the buckets below the vendors that are providing solar thermal energy solutions or concentrated solar thermal technologies to deliver heat from renewable sources. And then the thermal energy storage systems in the red buckets can be divided into those used for district heating. Those you can find them to the left, and then to the right for heating and cooling systems for industries and buildings. And then, which is where we will focus mostly today, the lower bucket, which is test for the management of heat in industrial processes. And the majority of these systems and these vendors, as we'll see on the next slide, can be also used for grid scale heat and power management. And that's why it's the only bucket across both front the meter and behind the meter applications. So now taking a closer look to this slide and these vendors and technologies, I will try to summarize this a little bit, but I'll spend quite some time here trying to explain this framework. So on these first columns here to the left, we've categorized these solutions depending on the technology or storage of heat principle these vendors are working with. So TESS involves the storage of heat in one of three technologies. First, a sensible heat, which is basically the most common method. Sensible heat storage means increasing the temperature of the storage medium when charging the system and decreasing it when discharging the stored energy. So in general terms, sensible heat is advantageous due to its low cost, but the main consideration is that the losses are often increased at higher temperatures. Then we have latent heat technology, which involves the storage of energy in phase change materials. So thermal energy is stored and released with changes in the material phase. The most common phase change to exploit here is solid-liquid transition, and the most common material being used here are molten salts. So when a phase change material is heated initially, it behaves like sensible heat energy storage, and then the material's temperature is increased. However, once the transition temperature is reached, the material will continue to absorb that heat at a constant temperature. Then storing heat with this method offers an increase in energy density and a decrease in losses, and being so, phase change materials are the subject to much research, especially concerned with the integration of phase change materials for both heat and coolness storage. Last, we have the thermochemical heat, which involves storing heat energy in chemical bonds. So a chemical reaction is used to absorb the heat to be stored. This reaction can then be reversed to release that heat. And the most common reaction being used here is the hydration of salts. It is a newer approach that offers an even higher energy density than phase change materials, but is less advanced, so that's why there are less vendors in this space as well. So in principle, these systems can achieve very high efficiencies with very low losses over time. Then on the second column, we can see the storage medium, which, as the name implies, is the medium in which the heat is stored, which can be seen on this second column. There is a great variety of materials being used. And then the last aspect of the system configuration is the heater type on the third column, which is the way in which the heat is delivered to the storage medium. So the main common types here, as you can see there, is the electric resistance, which is a well-established technology, as you know, with minimal degradation over time and allows also for precise control of the heat. So it's suitable for applications that require rapid heating or cooling. And then also pack beds, which usually have a higher thermal energy density and provide a large surface area for this heat exchange. The vendors that you find here are classified then according to this system configuration, but then they are also ordered from top to bottom depending on the temperature ranges that they are operating with. Which, as we have discussed before, this is something very important to take into account, the temperature ranges at which each vendor is working with. So we indicated in colors which type of processes these test solutions are useful for, as we described in the first slides of the presentation. So the ones indicated in green are useful for low temperature heat processes between 150 and 400 Celsius in yellow, and more than 400 Celsius in red. So following those colors, you will have also an idea of which processes and industries these test solutions are useful for. And you can find more information also here in the reference in the bottom. And then you can find the power range and charging time of each of these systems and their technology readiness level. And last, on the last three columns, we indicate some of the things we have also been mentioning before. So first, the market at which each of these vendors works for delivering their technologies. As you can see, all of them will, of course, deliver these systems for industrial applications, and most of them can also be used at power grid level. And still, some of these solutions can also be used to be coupled with concentrated solar power systems and also for district heating purposes. And last, as I mentioned on the previous slide, this ability on the last two columns, this ability to receive heat or power as input to charge the systems, and their ability to release heat or power as well. So in other words, this capability of converting power to heat and or heat to power. And as mentioned before, this is one of the main considerations to be taken into account in this test technology for a specific system that you're looking to decarbonize. So yeah, hope that all made sense. And I think we will be moving now to the Q&A. So open to any questions there.
Great. Thank you so much, Darcy team, for presenting on today's topic. I just wanted to help out with the Q&A. So we can spend the next 10 to 15 minutes for the Q&A. Quick reminder for our Q&A session. If you have a question, click the raise hand icon and we'll call on you to grant you access to unmute. Then you must manually unmute yourself to ask your question. After asking your question, please go back on mute. If you'd like to ask a question in writing, please feel free to use the question box and we'll ask the question for you. And I'll help moderate the questions, so feel free to blast away the questions. I guess I could kickstart and motivate questions today. I guess question for Lindsay. I know that the CEC is starting to look into distributed hydrogen production and end use. And so question for you is, what do you think some of the opportunities and challenges are for distributed hydrogen at the, I guess, the project level and at the technology level?
Yeah, so I think one of the biggest, well, there are a couple of big issues. I think the first one is really making the manufacturing process of distributed hydrogen production systems economic. So, you know, again, as mentioned in the presentation, the reports from the DOE Pathways to Commercial Liftoff and the Fraunhofer Institute report give a lot of advice about mass manufacturability, modularly expandable subcomponents, and considerations like that can kind of create a learning curve similar to that we've seen with solar in the last decade, where you see the cost really coming down quite rapidly as that supply chain and the manufacturing capabilities build out. So I think that's definitely one concern if you're looking at that smaller scale of production. In terms of technology readiness and some of the bottlenecks there, or hurdles there, especially with these thermal processes like methane pyrolysis that we zoomed in on, I think there are a few concerns, you know, with each technology type due to the high temperature requirements of that conversion process, especially if you're looking to get very high conversion rates and get the quality of hydrogen that you would need for most applications. And you know, that can include materials limitations. So if you're looking at a thermal process, there might be some material limitations, and with existing materials that are easy to source, leading to shorter lifetime, as well as with catalytic type pyrolysis processes, where I mentioned the catalyst can basically just become a feedstock due to fouling and coking. And I know that the vendors that were highlighted on the slide, they're all working very actively in each of their respective buckets to optimize the engineering of those systems to, you know, to get around some of those concerns.
Great, thank you so much for that, Lindsay. I see a question from David Correll. If you can mute your microphone, might be a little bit. For me, Lindsay. Question from David Correll. He asks, do you have a feel for when the IRS will make its final determination on what type of CO2 reuse will qualify for the $60 per metric ton of tax credits? Maura, do you have a good answer to that?
Yeah, hi. Oh, thanks for your question, David. It's from David, right, Alan?
Yes.
So I don't have a specific answer to that that has been released by the IRS, but I do know that one key concerning factor about carbon utilization is the fact that we're trying to capture it to prevent it from returning into the atmosphere. And so the question of utilizing carbon dioxide to produce fuels was something that it was still being asked. I think ultimately also the CI score of the life cycle of the process will affect how what type of technologies can be reused so that we can achieve that $60 per ton tax credit.
Great, thank you, Maura. And a question from Steve Cardiff. I hope I didn't butcher your last name. His question is, in El Segundo, California, there are natural gas-fired electricity generators and wastewater treatment plant, which generates CO2. The El Segundo oil field is nearby and would be a potential site to inject and store CO2 if the geology and reservoir integrity were adequate. Has Darcy identified potential opportunities to utilize SoCalGas infrastructure for CO2 storage? So I can actually answer that. The answer is no, we didn't reach out to Darcy for that type of opportunity. SoCalGas RD&D, we are a ratepayer funded program. So primarily we conduct technology projects focused on benefits to the ratepayers. And a different unit within SoCalGas explores the business development side of these things. But SoCalGas as a whole is looking into CO2 storage, and I believe if you go to the SoCalGas sustainability website, you may be able to find more information on CO2 storage. I know that they are looking into CO2 storage in Bakersfield area, so you might be able to get more technical information on the website. But thank you for your question, Steve. Appreciate that.
Alan,
any other questions? Go ahead.
If I can quickly join there on commenting on this, if that's okay. I think, Steve, your question is super to the point, and there's a lot of interesting things about what you just mentioned. In California, there's a couple like very interesting hubs for carbon storage that are actually with active Class A well permits underway. The Carbon TerraVault project from California Resource Corporation is just one example of those. I think the interesting thing to consider here, as you mentioned, if correct geological factors are found, are that CO2 as a gas needs to be transported in supercritical mode. That would be highly increasing the density of the fluid so that it reduces its size drastically. For that, you can't really repurpose natural gas pipelines for CO2 storage, just because you would need very high pressure or a very large amount of CO2 to be transported in the same type of pipelines. Usually you would need a smaller pipeline. That being said, there's a couple of technology developers and lab projects that are trying to see if you could eventually repurpose a pipeline for the transportation of CO2 instead of natural gas. But I think also there's a number of pipelines already in place for enhanced oil recovery that can be leveraged for this specific use case that you're mentioning. And in particular, wastewater treatment plants are a great place to capture CO2 and also to produce clean fuels, such as renewable natural gas, with extra CO2 capture. So amazing question. Thank you, Alan.
Yeah, no problem. I see that there are a few hands raised right now, so I'll go ahead and pivot to some open questions through microphones. So I see Roman Madas has a question. So I'll go ahead and unmute you, Roman, and then if you can speak your question and then go back on mute so we can answer them. Thank you. Roman, you're unmuted. Do you want to speak?
Wonderful. Can you hear me now?
Yes. Yes.
Great. I work for Osmosis. We make gas separation membranes, and we've been tracking your interest in hydrogen blending in the natural gas distribution network quite closely. And we're very curious about what SoCalGas is thinking in terms of hydrogen deblending, both to produce pure hydrogen streams at the end use for customers, but also to produce very clean and pure natural gas streams for customers that cannot take hydrogen.
That's a very interesting question. So it sounds like you have a technology recommendation in mind. I personally am not the subject matter expert on deblending, but I feel that perhaps Lindsay or Nolan might have the technical expertise to comment on that.
Yeah, I can comment on it. So, obviously we work with a number of clients beyond SoCalGas, and this has been something that has come up in a number of conversations recently. We've actually done a research report that we published for a particular client that made this request, and also publicly on our platform. And Osmosis, I don't know who you are, but I'm trying to get a meeting scheduled with you guys. So let's make that happen. I think that it's a rather niche situation where you have companies that are looking at blending natural gas with hydrogen. It's very difficult thermodynamically and physically to deblend any kind of low concentration hydrogen methane admixture, and the economics doesn't work out for most scenarios. However, if we are going to be doing blending, there are a number of niche applications where it really does make sense, and so there is a market for that. And I think that any of the gas utility or midstream companies that are looking into blending really will have, at least midterm, a potential need for that type of technology. And there's definitely been expressed interest in the industry.
Thank you. Thank you.
Great. Thank you for the question, Roman. I'm also happy for the SoCalGas team to look into your technology as well. So, all of our contact information is there. Feel free to shoot me an email if you would like to set up a call just to look into the opportunity and further explore that. And then I noticed Bill has several questions for the panel of speakers today. So I'll go ahead and unmute Bill Leahy so that he can ask some of his technical related questions. Let me just find him on the list of attendees if he's still there. Bill, are you still there? I just unmuted you.
Yes, can you hear me?
Yes.
Bill Leedy, the Leedy Foundation. I'm in Juneau, Alaska. We've co-authored research papers for 20 years on the prospects for moving large quantities of renewable source energy as hydrogen in pipelines. I attended the webinar you did earlier this year with several of the Southern California gas companies on blending, and the Leedy Foundation helped to support a meeting yesterday, Tuesday, I guess it was, at RMI in Boulder, Colorado on, excuse me, pipelining hydrogen. Of course, we have the hydrogen embrittlement problem, and it's a difficult one. So I wonder if SoCalGas is supporting actively now or will be in the future R&D programs for novel kinds of line pipe, perhaps a hybrid of polymers and non-ferrous metals that would be highly resistant to hydrogen embrittlement and corrosion cracking, and also capable of being manufactured in the field on site in continuous length for pull-in rehab of the extant natural gas pipelines, billions of dollars worth of which you own, which would then make them compatible for safe and profitable long-term movement of large quantities of hydrogen, either blended or high purity. That's my simplest question. Thank you.
Great. Thanks for your question. The simple answer is yes. We recognize during the energy transition there are going to be a lot of opportunities in the hydrogen blending space, especially pipelines. So I'd be happy to connect with you at my email address provided to connect you with the right team within SoCalGas to look into that. We do have a gas operations research group that specializes in that, and that seems like something that they would look into as well. So feel free to reach out to me. Thank you for your question.
I'm happy to comment on the more, I guess, technical and non-SoCalGas.
Go for it. Yeah, go for it.
So Darcy's, we're working right now. Our focus is kind of understanding the engineering challenges with broader hydrogen project development and what enabling technologies are necessary and having that be accomplished successfully and economically and equitably. And obviously one of the big issues is material compatibility and existing material compatibility with introduction of hydrogen. So very small, very squirrely molecule. It can, you know, move into polymers. It can embrittle certain metals, especially, you know, lower quality steels. So we've identified a number of vendors and you know, researchers that are being done in this space to develop materials like fiber reinforced composite pipe, or you know, liners that go into systems, or piggable coatings that are made of hydrogen resistant nanomaterial. So there's a lot of different things that are being pursued to make this possible, especially to retrofit existing infrastructure, which obviously would be the best case option. In addition to that, obviously, a lot of the valves, the welding would have to be optimized as well to prevent leakage, since hydrogen is such a small molecule. But I think that research is well underway, and there's definitely a lot of interest in figuring out how to make that economically viable, and also to move through fairly complex permitting pathways to get those types of materials and liners approved for broader rollout.
Great, thank you for that response, Lindsay. I don't see any more raised hands, and I don't see additional questions in the Q&A session. I do want to give people more time to think about the questions that they would like to ask. So perhaps we can sit here for like a minute or two before we transition to the closeout slides. Any other questions, audience? Happy to answer them. I see we received another question from Yudakjo. His question is, are there any distributed hydrogen demonstration projects in SoCalGas network? So in terms of the topic that we're discussing, the answer is no, we don't have a distributed hydrogen demonstration project per se, other than our SoCalGas hydrogen innovation home, which uses electrolysis to generate the hydrogen and deliver the hydrogen to the point of use, which is the hydrogen home. So, I mean, yes and no, but I think in terms of the topic discussed today, I don't, I'm not aware that we have any distributed industrial hydrogen demonstration projects, which I think we may in the future. Bill, do you have another question? I see your hand is raised again. I wonder if that's from the previous hand raised, but I'll go ahead and unmute you anyways.
Can you hear me?
Yes.
Bill, may I have another turn, please?
Yeah, go for it. No, I mean, we're already here. Happy to answer any questions.
You have this wonderful panel assembled here. Yeah. We can't let them go quite yet. The ultimate in distributed energy resources is going to be when we are able to profitably access deep, hot, dry rock geothermal, which is ubiquitous on Earth. It's right down below our feet. If we could only bore deep enough, cheap enough to access it, now we don't need to pipeline hydrogen around. We make it from electricity wherever we can access that. Are you folks at SoCalGas tracking that? I was at the Geothermal Resources Conference, Geothermal Rising Conference in Reno earlier, and people are making progress in boring deeper, cheaper into that really hot rock so that we can profitably produce that. And then we'll make it wherever we need it. Are you tracking that? Thank you.
I can say I'm tracking it. I'm a big fan of geothermal, but the feeling that I'm getting is in California, it's not really a priority area for us, but I know for the rest of the nation, there's a big opportunity for geothermal. I think the last year, the DOE has been pushing out several competitive grants in that space, and I think that it is really exciting, right, to utilize the energy from the earth to provide energy. But I would like to defer to Darcy, see if they have any input on geothermal.
I actually do, if I can quickly join. Thanks for your question, Bill. I think there's one key factor to consider here, that supercritical hot rock is different than geothermal energy. It's one subsection within the geothermal energy space. And it's one subsection that needs some years still to go ahead. Within the geothermal space, you know, we have conventional geothermal, like the geysers that you have in California producing energy, where we see a lot of innovative technology developers that are helping also improve efficiency of those processes as they are. To your point, this is not all over the place. You can only do it in tectonic regions where there's high volcanic activity and heat is coming up on its own from the underground. But then we also have a lot of like technology developers that are focusing on the unconventional geothermal space. And within the unconventional geothermal space, super hot rock would be, I think, that one of three main categories within hot rock and super hot rock as two separate ones. And within the hot rock, we would have closed loop systems and open loop systems. I think to your point, kind of a backfiring question that I might have is that if you can produce energy on site that you would use it, why would you want to turn it into hydrogen and not use it directly from the heat that you're generating from the subsurface? Unless you want that hydrogen for like a transport fuel or something like that, that you would get it into a car or a vehicle or something like that. If not, I think there might be some energy losses from the geothermal energy production to your hydrogen production to your energy production that might not be more beneficial in terms of economics, efficiency of the process as a whole. And then lastly, unfortunately, one key feature to realize is that today drilling deep, hot enough is not really cheap, not really available out there. But there's a number of projects that are working to make this happen. And to your point, the Geothermal Rising Conference in Nevada is one of the biggest, and anyone that's doing something on geothermal is there. And I think there's a lot of very cool projects that we're seeing in that space. But to be ubiquitous, I see more development on the heating and cooling applications for geothermal energy right now rather than the electricity production. I think it's going to get there. It's just maybe this is not like a today thing. I don't know what you think. This is an open conversation, of course.
Ms. Serrado, I think your question, why would you make hydrogen, is for transportation fuel, for all modes, everything from aviation to your car and mine. Thank you.
Yeah, I agree. Yeah.
Great, thank you so much for that question, Bill. Happy to answer any more questions. Audience, if you have any more questions, feel free to either, pop it in the chat or raise your hand and I can give you a call out. So I have a question for Juan. I do have a question. So when should a facility owner consider a TES solution, whether it's constrained by gas lines or volatile prices? Yeah, when should they consider a TES solution?
Thank you, Alan, for your question. Well, it can be used either for industries that are subject to any emissions regulations, of course, or carbon reduction targets. But they can also be used for industries that require temperature control in their processes, of course, as we said, like in food processing or chemical manufacturing or material processing, that can benefit the TES to manage and optimizing that heat and cooling loads. And then also, of course, apart from the industrial processes that we've discussed through the presentation, also any facilities with high heating and ventilation or air cooling loads that want to manage that would be useful as well. And then for that's specifically answering to what is related to thermal energy storage, but then it can function as any type of energy storage, of course. So for peak load management, for load shifting, or to increase the reliability on areas where the power grid is unstable, that would work as well. I mean, it has the same capabilities as any other energy storage system would provide, with the capability of storing energy and using it later for any of those purposes, as I mentioned.
I see. And, I've done some work in the TES space, and I'm curious to know what do you think some of the challenges to adopting TES is? I think there's a huge opportunity to utilize waste heat, and it's just such a shame that it hasn't, received the market penetration that it has yet. So, either from a technology standpoint or a market development standpoint, what do you think are some of the challenges that TES has to overcome?
Yeah, so the main challenge is with heat in general, it's technically it's very difficult dealing with losses, and that's why it's very common to have high losses on these systems, and that's why it's difficult for them to be on the market today. I mean, we're only seeing now the first pilots of these technologies, and the main challenge is related to that. And then specifically for the US market, I think producing heat or generating heat in industries, it's cheap today. So also fighting against that equation, economical equation, it's also very difficult in markets like in the US. In other markets like in the European market, where heat generation, generating heat is more expensive, it's easier to have these systems deployed and in the field. And you can see that very easily, not yet in industrial applications, but for example, when it comes to district heating, that these solutions are already being used for that market in Europe.
Great, thank you, Juan, for the insight. I appreciate your thoughtful response. I do see that we're coming up on about time, so I just wanted to take this opportunity again to thank our panel of speakers from Darcy today, And I also wanted to thank our audience for their time today. The recording will be, and just a quick FYI for the audience, the recording will be available on our website soon. Be sure to check our LinkedIn for an update on when it's ready. You'll be receiving a survey request in your inbox soon. Please take a moment to fill that out. Your feedback will help us improve our webinar and help us select topics that are of interest to our stakeholders. Remember, at SoCalGas RD&D, we strive to identify transformative energy solutions and build them, share them with you and the world. And so thank you again for your time. Have a great one. I will be concluding the webinar now. Thank you so much.